All right, well, we've seen how the conditional expectation can be thought of as a best predictor, right? Given X, given a random variable X, the best prediction we can make of Y is the conditional expectation of Y given X. And we actually saw that how that plays with the variance, ANOVA variance formulas, that the worst case scenario, the worst case error that we showed was, so the error in making that prediction is what our original error would be if we ignored the information in X, but we have a better prediction by getting rid of our uncertainty about how Y relates to X. Well, in statistics, a lot of times what we're doing is we don't have generically, we might not be able to calculate the conditional expectation of Y given X generically. And so we actually consider the question of, well, not just the best predictor using X, but what's the best linear predictor? So a predictor of the form G of X equals A plus B times X. So capital X. So this is now going to be a function of X, but it's a specific linear form. We call it a linear predictor. So we're going to ask the same question, but we want to say, okay, let's suppose XY have mean 0, variance 1, covariance rho. Then what is the minimum? What minimizes the same expression, the mean squared error, which is going to be the squared deviation of Y from A plus BX. So we're trying to predict now Y as a linear function of X. And let's note, just before we do this, that the covariance of Y minus rho X with X is covariance of YX minus rho, covariance of X with X. Covariance of YX is rho, covariance of X, or variance of X is 1, so this is actually 0. So therefore, if we write R, the remainder, in other words, so R is how far off we are in our prediction. So this is minus A plus Y minus rho X plus rho minus BX. If we do this, then the expectation, the expected error is minus A. And the variance of our error, right, which is the variance of minus A plus Y minus rho X plus rho minus BX. So the constant doesn't affect anything, so it's variance of Y minus rho X plus rho minus B squared variance X. And the mean squared error is the expectation of R squared, right? That's the definition of mean squared error. Well, expectation of R squared is a squared plus rho minus b squared plus the variance of y minus rho x. And so to minimize this, in terms of A and B, right? These are the only variables we have at our disposal. We would take A equals 0 and B equals rho. And the mean squared error of that prediction, rho x, is the variance of y minus rho x, which is 1 minus rho squared. So in general, for arbitrary means, mu x, mu y, arbitrary variances, sigma x squared, sigma y squared, and covariance, we're writing a sigma xy, the best linear predictor of y given x is the mean of y, but we adjust it by the covariance the variance and how far x is away from its mean. And the mean squared error in this case is just as before, but it gets multiplied additionally by the variance of y. So this is a very important formula, especially when we talk in the multivariate normal or the bivariate normal distribution. But it turns out that this applies generically to all joint random variables, is that the best linear predictor of y given x, in general, it's the conditional expectation of y given x. Well, no, the best predictor is the conditional expectation of y given x, but if we can't use a generic function, if we're doing a best linear predictor, we only have the expectations, variances, and covariances to work with. And so this has an important interpretation, because the covariance really just measures linear dependence. And given the way that we're describing this here, it actually in some sense captures all of the relevant linear dependence in a random variable, in a joint distribute between two random variables. Because if we're trying to predict one random variable by the other using a linear function, we see that all of that, in some sense, the best linear predictor is capturing it through what's called through the covariance. And the covariance, the correlation is the covariance normalized by the standard deviations of the random variables.